Hello, Assalamu alaikum warahmatullah. So I'm going to explain the correctness of Huffman's algorithm. Basically, it's the proof of Huffman's algorithm and how it works. So basically, Huffman's algorithm says that it's like we can consider like Huffman. What we're trying to prove is using Huffman's algorithm, we get the best optimal solution using Huffman's algorithm for a compression. Basically, we can get the most optimal solution. What does most optimal solution mean here? The most optimal solution means that the most less frequent, right? The most frequent things will be higher up and the less frequent things will be lower down in the tree, right? So we have this Huffman code tree here, right here, as you can see. In this tree we want the more frequent ones to be higher up in the tree and the less frequent ones to be lower in the tree. So the lower frequencies will be lower in the tree and the higher frequencies will be higher up in the tree. And this is the algorithm that we're using to make the Huffman tree, basically using a min heap. So here the optimal solution, what the claim is saying that consider two characters x and y with the lowest frequencies, then there is an optimal tree in which x and y are siblings at the deepest level of tree. So let's say we have a tree that looks like this. So we're saying, let's say there is x and y, there are two lowest frequency elements, nodes in this tree, let's say 15 and 25, which are the lowest ones. We can find the most optimal tree. There is an optimal, like the claim is saying that there is an optimal tree such that x and y will be on the bottom most part of the tree. Basically, this is what the claim is saying. So we can always use Huffman's algorithm to find that, to eventually, after using Huffman algorithm, eventually at the end of this Huffman algorithm implementation or running of it, x and y, which are the lowest frequencies, will be siblings at the deepest level of the tree. This is the claim. So how do we prove it? We prove it using an exchange argument. It's like a type of proof. So we first assume there is an optimal tree, like a prefix code tree. Prefix code tree is that tree that I just showed you. This is called as a prefix code tree, which is explained earlier. I'm not going to explain Huffman code or Huffman algorithm or the prefix code and how that works. I'm just going to explain the proof here. So let's assume T to be some optimal prefix code tree for a uh, particular sequence or input we have. So let A and B be two random siblings at the deepest level of tree. So it doesn't have to be the lowest frequency, it just has to be the two deepest ones. So we're assuming that T is optimal, firstly. So you're assuming T is optimal, that's the first thing we're assuming. Secondly, we're saying A and B are the deepest level of the tree, right? A and B are siblings at the deepest level of the tree. Now we will show in some way, we will convert this tree into another prefix tree where X and Y are siblings at the deepest level without increasing the cost. So we will not increase the cost. So the cost is mentioned as B of T. So B of T literally is saying, what does it give? It gives it the cost. What does the cost mean? The cost is the whole cost of the tree. So here, for example, if you add all these things, we get the cost of the whole tree. So how many, like there are 2 bits here, 2 times, so we use 2 bits for the character D, and we have the frequency 40. So 40 times 2 we get 80, and then the same thing, 2 times 50 we get 100. We add all these things, and there is 3 times 25 and 3 times 15. We add all these, this is what we can consider as the cost. One example of considering as a cost, right? We add all these things and then we'll get the cost in a way. So the cost of this tree is written as B of T. That's one way of writing. That's the way of writing the cost of a tree. So we will say that we will convert the optimal tree that we are assuming here into another prefix tree, which is also optimal. Right? This is what we're gonna prove. Which is also without increasing the cost. What does without increasing cost mean? It's also optimal. That's what it means. So let's look at the example. So we have, what we're going to do is we have x and y. As we said, x and y are the lowest frequencies. So x and y have the lowest frequencies, and what we're trying to do is we need the bottommost to be the lowest frequency. So x and y should reach the bottom, right? And that means that we have an optimal solution, right? But we are assuming we have t, okay, which to be optimal solution. I think it's getting a bit confusing, but I think when we go down and explain, it become easier. So forget the right side, we're looking at the left side right now. So here we have this tree, right? We have this tree called T. We called it T earlier, and we assumed it to be optimal. It's an optimal solution. It's some arbitrary optimal solution we have, right? So we look at this tree and we say, okay, we have this tree and it is optimal. And this tree has the values x, it has the value y, and it has the value a and b. Okay, and a and b are the lowest, like it's at the deepest level of the tree. So A and B are siblings at the deepest level of the tree. Okay, so now let's say A and B are not the lowest frequencies, right? Let's say they are not. So we are assuming they are not. They might not be, but we are assuming they are not. Let's say maybe they are not, right? But T is an optimal solution. So we have X and Y. So we switch X with A. That's the first step we do. So we swap these two both and we get A here and X over here. We swap these both. So what we're trying to do, we have X and Y, which has the lowest frequencies. Lowest frequency should be on the bottom of the tree. So we're trying to make that work. We're trying to make that happen and see what happens and see if it becomes still optimal or not. So we have A, we swapped with X, and we have a new tree here, which is called T dash. Right? We have a new tree called T dash, and in this new tree, A is in the position of where X was, and X is in the position where A was. Right? So we've swapped that. If you look at this, this has B of T. B of T is the cost of this tree, the cost of the whole tree T, right? And then we have B of T dash, the cost of this whole tree. So if you look at this tree, okay, this tree has a particular cost. When we swapped these two, okay, when we swapped X and A, what we did is we made it a better solution. How do we make it better? We made it more optimal because X is one of the lowest frequencies. And when X reached the bottom of the tree, what happened? It became more optimal. That's why it is like it became more optimal or equally optimal. It won't be less optimal. This is the point, right? It will become more optimal. So the cost of the secondary T dash will definitely be less than or equal to the cost of T. Got it? That's what's written here. The cost of BT dash is less than or equal to the cost of BT. This is what's written here. Alright. Now we still have Y, which is the second least frequency. Right? Y is second least frequency. So now we swap Y with B. Right? We swap these two. Okay. We swap these two, so we get Y in position of B and B in the position of Y. So that's what we did here. B becomes here, Y becomes here. So what happens here? Y is one of the lowest frequencies, right? So when we brought it to the bottom of the tree, okay, it became more optimal. It will become more optimal, or like the cost becomes less. Either it becomes less or it becomes the same. If they are both equal frequency or something like that, it becomes the same, or it becomes the cost becomes lower, right? And therefore that's what we're saying. The cost of this whole tree is less than or equal to the cost of this whole tree. That's what's written over here. So the cost of BT dash dash is less than or equal to BT dash. It can be equally the same cost or it can be lesser to the cost. So now the proof is in the formula way. So we're trying to say that we're trying to prove this basically if this is greater than or equal to 0. Why would this be greater than or equal to 0? So as I explained over here, the BT, okay, is the first tree, the cost of the first tree, minus the cost of the second tree, right? So if this is bigger than this, if the cost of the first tree is more than the cost of the second tree, that means the result of this whole thing, this minus this, BT minus BT dash, will be a positive number. It will be greater than 0 or equal to 0, right? Or if it will be equal to 0 if they're both equal, because the cost is equal, right? So if we do this minus this and we get it is greater than or equal to 0, that means we have a more optimal solution or equally optimal solution. And how are we proving this? We're proving this using this formula. Okay, so I'll just explain what this formula is. So we're assuming this, by the way, we're assuming f of x is less than or equal to f of y and f of a is less than or equal to f of b. This is just assumptions. We're just assuming these things. It's kind of taken, let's say, and we know f of x is less than or equal to f of a and f of y is less than or equal to f of b. This is a given. Why is it given? What does f mean? Is the frequency, right? So we are saying x and y are the lowest frequencies, right? That's what we said. So if x has the lowest frequency, that means a should have a higher frequency than x or equal frequency. One of them should be true. It's either less than x has a lower frequency than a or equal frequency as a. That's the reason why we can say this is true. Same thing for this, y and x are the lowest frequency, so y should be less than b. The frequency of y should be less than b. That's why it's set as given. So f, I said, is the frequency of a particular character. F of c is frequency of c, and the capital C is all the characters that we are compressing. Basically, we are trying to minimize it, right? What is Huffman algorithm basically doing? We're trying to make a compression, right? We're trying to compress a whole input string into a less costly string, basically. So the C is the list of all characters, and f of c gives us the frequency of a particular character in that character list, and the dt of c gives us the distance in the tree T of the character C. So what does that mean? So we have this tree, for example. So in this tree, let's say we are trying to find dt of y. Dt of y will be 1, 2. So the distance is 2, for example. So that's what it means. For example, if you want to take the distance of 1a, it will be 1, 2, 3. That's the distance, right? So the distance should be higher for lower frequency, right? So for example, here x is the lowest frequency. So the distance should be bigger in this distance, which is 3, should be bigger than a, for example, because a has a higher frequency and x has a lower frequency. So this distance should be bigger than this distance. This is what you need to understand. So here the cost is basically the frequency times the distance, basically. So as I explained earlier, in the previous here, what I explained the two bits times the frequency. What is 2 bits? Is 1, 2. That's basically the distance. Distance is basically the number of bits here. Number of bits is basically the distance. So I do the distance times the frequency. So 1, 2, 3 times the frequency, right? That's the same thing. That's how we calculate the cost. So that's the cost formula. So now we have the cost of the whole. So this FC DTC is the cost of one single character. That is C, the cost of one single character in that tree. And B of T, the cost of the whole tree, is the sum of all those characters in the tree. So we have the characters, all the characters in the list C, capital C. We find the cost of all of them and we sum it to get the whole cost of the tree T. Hope that makes sense, right? And then we have the second tree, which is T dash. We do the same thing for that. So it's the frequency of C times the T dash of C. And then we do this minus this, we get this minus this. I think that makes sense. And then we take, so there are probably there is more characters in this whole tree, but if you subtract this minus this, nothing else moved, so we don't need to consider them. We can just ignore them. The only thing that moved is x and a. So as you can see, we are only considering t dash, we're not considering t dash dash, which has y also moved, y and b also moved, but here in this t dash only x and a moved. So x came here and a came here. It's only x and a that moved. So we are only considering the frequencies and the distances of x and a, right? So in this here we have the frequency of x times the distance of x plus frequency of a times the distance of a. That's this whole thing, right? That's that whole thing. Let me just, so this red part here is the red part here, right? And then we have this part here, which is written inside this part here, right? So this is the frequency of C, frequency of x times the distance of t dash, as you can see, the dash of x, plus the frequency of a times the distance of t dash in a. And so we get this formula. Now what do we do? The next step, what we do is basically we have to change this. So distance of t dash of x, distance t dash of x is equal to distance of t of a. Okay, so let me just explain that. What does that mean? So distance of t dash of x, so this distance, basically this distance from here to here to here, that distance is equal to the distance of a in this tree, because a was over here. So these two are equal because we swapped x and a. So x is in the position where a was before, right? And for that reason, this distance, this distance t dash of x is equal to distance of t. As you can see, there is no dash here, so distance of t of a. I hope that makes sense. And the same thing over here, distance of t dash a is equal to distance of t of x, right? So we swap them, and we there is a minus sign here, we put minus everywhere, so we get minus minus minus. And then we take them as groups. We take the groups, so we take f of x, and f of x. We put them together, and we take f of a and f of a. We put them together, and then we get the small formula we have over here inside here. This thing that's written in blue, and then after that we get this final state, we get this final state. And what can you see in that final state? The frequency of A minus the frequency of x times the distance of A minus the distance of x. So what does this mean? So the frequency of x we know is lesser than the frequency of A, right? Or lesser than or equal to, which means the subtraction, the f of A minus f of x, should be greater than or equal to 0. That's what's written here, right? And then we have dt, the distance of A, okay, should be greater than the distance of x, right? Of t in x, which means this minus this should be greater than or equal to 0, right? So distance of A is greater than, so distance of A is greater than distance of x. Wait, that doesn't make sense. Yeah, distance of A, yeah, sorry, no, true. The distance of A, this is the distance of A, should be greater than the distance of x, right? In the tree T, we're talking about the tree T. So in this particular tree, in T, distance of A should be greater than distance of T. Yeah, that makes sense, my bad. So that means this minus this should be greater, this minus this, the total thing should be greater than or equal to 0. So if you have something that's greater than or equal to 0 times something greater than or equal to 0, the final output should be greater than or equal to 0. And that means the new solution, the new tree we have, bt dash, should be equally optimal to bt, as in the new tree t should be equally optimal to t or more optimal than t. And we can do the same proof in, since b minus t is greater than or equal, t is at least as good as t, t dash is at least as good as t, so t dash also should be optimal. So similar conversion we can do from t dash to t dash dash to show that t dash dash is also optimal. The same thing can be done. We can do the same thing, bt dash minus bt dash dash, to get the same result. So what we're saying is, so moving x to the bottom and moving y to the bottom gives us an optimal solution. And this is basically how we prove it. I hope that makes sense, inshallah.